Right, this test is on rotational motion, right? So on rotational motion, under this test we'll be covering about motion equations, moment of inertia, and torque. So those are the subtopics that will be covered under rotational motion. Then there will be a second test also to cover the remaining part of the rotational motion. So if you are familiar with linear motion equations and how to apply F equals ma, so it is similar here. There's no difference. Only difference is in the linear motion, the motion is in a linear line, right? Is on a line. But here we have to consider the angle that an object rotates. So instead of the distance that traveled, here we are talking about an angle, the angle that the object rotates. That's all we have to consider, right? So that's the only difference there, right? We'll move on to the first question. Units and dimensions of angular acceleration is. So similar to linear acceleration, angular acceleration is, so linear acceleration is rate of change of velocity. Here, angular acceleration is rate of change of angular velocity. That's why we always have to consider about the angle, right? So they're asking about units and dimensions. So you know that the scientific unit, the SI unit to measure the angle is radian, right? I'll just briefly explain this. SI unit is radian to measure the angle. So this equation. So this is the length of a arc, and this angle is theta, then the radius. So from this we can see that S divided by R is equal to the theta. So this is what we call angle in radians, right? So this ratio S divided by R is a constant for a given angle. No matter the size of the arc, this ratio is a constant. So that is how we defined the radian. So both S and R, those are lengths, right? So if you think about dimensions of angular displacement, it should be L divided by L, which is 1, right? So angular displacement doesn't have dimensions, it is just 1, right? Okay. So for the linear acceleration, it is ms minus 2. For the angular acceleration, instead of the length, it should be angle, measured in radians per square second, right? Instead of meters, we just use radians. So for any quantity, that is what you have to do. If it is given that is a angular quantity, so instead of meters, it is radians. So this is the unit. If you think about dimensions, radian means no dimensions, dimensionless, and the S2 minus 2, so it should be S means time, seconds, t minus 2. Radian doesn't have dimensions, so this is the dimensions and this is the units of angular acceleration, right? Okay, second question. Rate of revolutions increases from 300 revolutions per minute to 1500 revolutions per minute within 10 seconds. Its angular acceleration is, right? So the angular velocities are given in RPMs. So you should be able to know, you should know that how to convert RPM into radians per second, right? So first we have 300 RPM. So how to convert this? 300. R means revolution, right? One revolution. So in radian it is 2 pi, meaning 360. So instead of R you can use 2 pi per minute. So you have to divide this by a 1 minute. 1 minute means what? 60 seconds, right? So instead of 1 minute, just put 60 seconds. So 5 times 2, 10. 10, 5. So it is in radians and per second. So 300 RPM is 10 pi radians per second. So this is how you do that conversion. Then it is increased to 1500 RPM. What do you do? 1000 R means 2 pi per minute. Instead of minute, just put 60 seconds. So what do you get? 50 pi radians per second. Right? So 1500 RPM means 50 pi radians per second. Right? So this is omega naught and this is omega. This is omega naught, this is omega. So angular velocity is what? Rate of change of angular acceleration, rate of change of angular velocity. So what is the change of velocity? Omega minus omega naught divided by time. So omega is 50 pi. Omega naught means 10 pi divided by time. Time is 10 seconds, right? So 40 divided by 10 is 4 pi. Rad per square second. Get it? Rad per square second. So you can understand that this is similar to linear motion, right? Linear motion equations. So the answer should be fourth one there. Right, third one. An object starts rotating at 2 rad per second under an acceleration 4 radians per square second. So the initial angular velocity is 2 rad per second. Have given the acceleration 4 rad per square second. So what they ask is angle that the object rotates within first 2 seconds. Within first 2 seconds means from t equals 0 to t equals 2 seconds, right? So they have given initial velocity, angular acceleration and time. So you need to find the angular displacement. So it is like, so when you think about this data, you should remember this equation, right? Time is given, acceleration given, initial velocity given, right? So if we cannot directly write the equation related to angular quantities, you can use this equation. Then write the equation. So instead of S, you can put theta, the angle, right? Displacement means angle there. Initial velocity, time plus half angular acceleration t squared. So omega naught is 2, time is 2 plus half, alpha is 4, time is 2. So 2 is squared. So you get 4 times 2, 8, 8, 4, 12. You get 12 radians, right? So the angle is 12 radians. So that is the angular displacement, is 12 radians. Third one is the answer. Sorry, fourth question. A wheel at rest is submitted to an angular acceleration 4 radians per square second. So initial velocity 0 and angular acceleration is 4 rad per square second. Angular displacement of it within the 5th second is. So what does it mean? Within the 5th second means, if you take a timeline, so this is t equals 0. Within 5th second means time from 4 seconds to time from 5 seconds, right? So we have done similar questions in linear motion. So what they ask is angle that rotated within this 5th second means time between 4th and 5th seconds, right? So to find this, you have to apply the equation from here to here minus here to here. So let's say angle from here to here is theta 1. Here to here is theta 2. So when you subtract these two angles, you can find this. So there's no any other way to find this, right? So this is the way. So we did similar questions in linear motion, right? Okay, so initial velocity is 0. So I can write this equation. This is the equation, right? Half at squared. Ut is 0, u is 0. So related to this, half a means alpha, then time squared, right? So first find find theta 1. Theta 1 is half, alpha is 4, uh, t squared. Time there is 5, right? 5 squared. So we get 2 times 25, 50. 50 radians. Then we need to find theta 2. Half alpha t squared. Half alpha means 4. So from here to here it is 4 seconds. What do you get? 2 times 16 is 32. So the angle between 4 to 5 seconds is, let's say, delta theta. So you need to subtract this, theta 1 minus theta 2. So 50 minus 32. What do you get? 18 radians, right? So the angle within the fifth second is only 18 radians. It is not the angle from here to here, right? It is angle within a 1 second actually, within this. Angular velocity time graph for a wheel which has an increase in angular acceleration is. So the fifth question, right? So you can think this in terms of, if it is difficult to think in terms of angular velocities, you can think in terms of linear, right? Then you can convert. So angular velocity, omega t graph, and they say increase in angular acceleration. So if you think about a omega t graph or a vt graph, the gradient of the graph gives us what? Acceleration, right? Here it is angular acceleration. So gradient is equal to angular acceleration. If it is a vt graph, it is just linear acceleration. But for omega t graph, it should be angular acceleration gradient. They say angular acceleration increases. So what does it mean? Gradient should increase gradually. Gradient means the slope. So as the time goes, gradient is increasing like this, right? Like this. You can see that slope is increasing. So the graph should be like this, right? You can check that. Just draw a tangent here, the gradient of this tangent. So if you consider the gradient here, this has a larger gradient, right? So that you can see gradient is increasing, right? So that's what it means to increase the angular acceleration. So the answer should be third one there. Sixth question. 3-point masses 4 kilogram, 3 kilogram and 1 kilogram are placed on y-axis. So let's say this is the y-axis and you have the x-axis. So the masses are 4 kilogram is placed at y equals 4. 4 kilogram is here. And the coordinate here is x0, y4. This length is 4, right? Then 3 kilogram at minus 2. Let's say minus 2 here. So x is 0, y is minus 2. So it is 3 kilogram here. Then this coordinate 0 minus 4, they have placed 1 kilogram. So what they ask is moment of inertia of the system around x-axis is, right? So this is the x-axis. We can say Ix, right? So how do we find the moment of inertia? Mass times distance squared. That is how we find the moment of inertia. So for each mass, you have to do the same thing. Then you just have to add all those in order to find the moment of inertia of the whole system. So when you're thinking about distances, the distances should be normal distance, right? So this is the axis. To the axis, this mass should be at an, this distance measured is normal to the axis. Okay, so for this mass, 4 times mass is 4, distance is 4 squared. You just have to add these. Plus, for this one, 3 kilogram, distance is 2, 2 squared. Plus, this one, 1 kilogram, distance is 4 squared, right? Then you just have to add all these. So here we have 16 times 4, 64. 4 times 3, 12. 4 squared means 16. So when you add these, 28, 12, 92, right? So you can see the unit should be kilograms per square meter. Sorry, kilograms is square meter. Mass times distance is squared, right? So it should be 92 kilograms per square meter. Okay, so the answer should be third one. So you know that for a rotating object, the inertia of that object, inertia means the reluctance to move, right? So for a linear motion, inertia only gives us from the mass of that. Mass of the object determines the inertia. But for a rotating body, only mass is not enough. You have to consider the mass distribution as well. That's why it is mass times distance is squared, right? Mass times distance to that particle from the axis is squared. Because you have to consider the mass distribution as well. So if you have like two objects with the same mass, but one object has a higher mass distribution, so that object has a higher moment of inertia, right? But both have the same inertia when you're thinking about linear motion, because the masses are the same. But for rotating body, you have to consider the mass distribution as well, right? Okay, so the answer to that question is third one, right? Right. Seventh question. Mass ratio between two rings is 1:2. So let's say ring 1, ring 2. So we know that moment of inertia of a ring is measured using mr squared, right? So all the mass is concentrated to the circumference of the ring. It is only all the mass is at a distance simple r, right? So can get this equation for a ring. Okay, so mass ratio is given as 1:2. 1:2. Diameters are given as 2:1. So if the diameter ratio is 2:1, ratio between radius also should be 2:1, right? So here the diameter is 1. Here the diameter is 2 times. So the radius also should be 2 times. Okay. But here what you need is r squared. So the r squared value is just square these values. 4:1. Right. To get the moment of inertia, these are the mass values, should be multiplied by r squared values. So here 1 times 4 ratio is to 2 times 1. So what you get? 4:2, meaning further you can simplify this to 2:1. So 2:1 is the ratio of moment of inertia between the two rings, right? Fourth one is the answer there. Right, eighth question. On each vertex of a light square, with side length capital L. Okay, so we have a square, right? Actually, it is a light square, means these does not have any masses. Only at the vertices have masses placed. So each mass, simple M, and the length is given, capital L. Okay. So what they ask is moment of inertia around an axis which goes through one side of the frame. One side means you can consider either this side or this side or any one of these four sides. So I'll just consider this side. So what they ask is, this is the axis here which I am consider, this is the axis. So what they ask is around the axis moment of inertia. So you can see to this mass from this axis the distance is 0, right? So for these two masses does not create a moment of inertia around this axis because there's no distance to those masses. But when you consider this mass, then the distance is L squared plus, understand that you are considering distance that is normal to the axis you consider, right? So when you draw normal to the axis, distance is capital L. Here as well, so this is the axis, normal distance, this one, M L squared. So you get 2 ml squared, right? So the answer should be third one. So you have to understand these clearly. Then these are not that complicated, right? Very simple. So this distance means that distance is always perpendicular to the axis which you consider. Ninth question. A and B, two circular plates with the same thickness have moment of inertia I1 and I2 around axis through their center normal to the plates. And they say that I1 is larger than I2, right? So the question, in the question they have given options. They say that A, mass of A is higher than B. Then they say radius of A is higher than B. Then they say B reaches rotating to the bottom first. So they have given a bunch of sentences, right? So I1 means I can say like so for a plate, moment of inertia is half mr squared, right? So let's say mass of that first plate is m1 and radius is r1. So here you get m2 r2. Let's say like that. So from this m1 r1 you can get rid of half greater than m2 r2 squared, right? So this you can gain. But this does not mean that m1 is larger. You cannot consider only m1 and say that moment of inertia larger. Radius could be a very low value, right? So same goes to the radius. Even though the radius is a larger value, m1 could be a small value. Then this whole thing could be smaller, right? Moment of inertia could be smaller. So to consider the moment of inertia, you have to consider both mass and radius. So the first two sentences are wrong, right? Then if we consider about time, so this has less moment of inertia. B has less moment of inertia. What does it mean? Inertia less means, just remember that, right? Inertia means it is easy to roll over. It quickly rolls over, right? So this has less moment of inertia. So what does it mean? This will reach the bottom first. So B reaches the bottom first, right? Because it can easily rotate, rolls and comes to the bottom. So that is what inertia means, right? inertia is reluctance to move. So this has less reluctance to move, right? So the plate B rotates easily compared to the plate A. So the C is correct. So the answer should be third one there. Right. So the remaining questions are from based on torque, right? Right. 10th question. A solid cylinder, a solid cylinder with mass 50 kilogram. So 50 kilogram and radius 0.5 meters is free to rotate around its axis. So the axis means, so if you think about this cross section of the cylinder, this is the axis which goes through there, right? A string is wrapped around it. A string is wrapped around this one. And they have given the moment of inertia. You should know this value, right? For a solid cylinder, equation to find the moment of inertia is mr squared divided by 2. Okay. Tension of the string. Then they say you need to give this an acceleration of 4 pi rad per square second. So this angular acceleration should be given. So what they ask is, in order for this to be given, tension required. They have given the radius. I'll just consider radius as capital R, right? Right. So how do we solve this? You need to find the tension, right? Okay. So similar to F equals ma, right? So F means unbalanced force. So when it comes to rotational motion, you have to consider the unbalanced torque, right? Instead of F. So then instead of m, you have moment of inertia alpha. Simple A is alpha, right? So this is the equation we use to find this, right? So when you apply this one, so let's consider there's a direction that you have to apply that. So this is useful when you are doing a complicated question, right? This is not a complicated question. But if you are doing a very complicated question, you need to consider these directions precisely. Okay. So this is, we are talking about torque. Torque means moments, right? So to this direction, and I'm considering moments around the axis. So let's say O. Okay. So how do you find the torque? Force times, tension is the force times distance, perpendicular distance. That is capital R. Okay. So I is what? mr is squared divided by 2. They have given that. Then alpha also is given. So if the equation seems, problem seems complicated, it is better to only use, first just use symbols, right? After that you can substitute and get the answer. If you substitute values here at first, it will be a bit complicated, right? So it is better to get the answer first in symbols, then quickly you can do the substitution, right? So here I'm going to cancel R. So T is equal to mr divided by 2 times alpha. So tension is what they ask. Okay, now just substitute values. So mass is 50, radius is 0.5, divided by 2 times alpha is 4 pi. Okay. 2, then this 2, this is half, right? 2 times half is 1. So you get 50 pi Newton, right? See that? It is simple and nice, right? Doing like this. There are many questions like this in rotational motion because there are too many variables there, right? In these equations. So it is better to simplify. First simplify. using symbols only. Don't substitute values first. Once you get that, then do the substitution. So that is better, right, for most of the questions. So the answer should be fourth one there. Sorry, 11th. A wheel at rest is given a torque 100 Newton meters. So torque is given as 100 Newton meters. And angular displacement, initially it is at rest. So omega naught is 0. So it does the displacement 200 radian, and the time it takes is 10 seconds. So that is what they have given. Time it takes is 10 seconds. So these values are given, right? So what they ask in the question is moment of inertia around the rotational axis of the wheel, right? So what they ask is I. Okay. So how do we do this? So we have this equation tau equals I alpha. Then for these ones you can apply a motion equation. So if you know torque is given, torque equals I alpha, right? So if you can find alpha, then you can find I. So let's find alpha using motion equations. So there are some data here. So which equation do you think about this? So this displacement, time. So we need to find alpha. Initial velocity is 0. So you need to remember this equation. Half alpha t squared. Omega naught t is 0, right? Omega naught is 0. I didn't substitute that. So half alpha, time is 10. 10 is squared. Displacement is given as 200. Right? So there's 100 divided by 100. So we have alpha here. Then this 2 brings to the opposite side. Cross multiply. 2 times 2, that is 4. 4 rad per square second. So this is the angular acceleration. Right? So easily we found that angular acceleration. Then just apply tau equals I alpha. So torque is 100. I is what we need to find. Alpha is 4. What is that? I is equal to 25 units kilograms per kilogram meter squared. Right? So this is the moment of inertia. So the answer there should be first one. Right. 12th question. A thin uniform rod with length 2L. So we have a uniform rod and its length is given as 2L. And mass, simple m, is rotated around its axis through its center. So the axis goes like this, right? Through the center. Normal to it. At a uniform acceleration till the angular velocity is omega within a time period simple t. And it gains this omega angular velocity within simple t. Right? Torque applied on it. Right? So initially this is at 0. Then it gains this angular velocity omega within a simple t time. Right? So what do we apply here? So here what they ask is torque applied on it. So torque is equal to I alpha, right? I alpha. So in order to find the torque, we need to find I, then we need to find alpha. So using these ones, we will be able to find alpha. So I'll just apply this equation. Omega naught plus alpha t. Initial velocity is 0. Alpha we have, let's say alpha, angular velocity is alpha, acceleration is alpha, t, and the final velocity omega. So alpha is equal to omega divided by t. We'll need this one, right? Alpha we found. Then we need to find I. So how do we find I? For a rod which goes through, if the axis goes through the center of it, perpendicular to it, equation is half ml squared. Remember, you need to remember these equations, right? So 1/12, so mass is just mass, simple m, but the length they have given as 2L, right? Capital L means total length of the rod. Here it is 2L. 2L squared. So what do we have? Here you have 4, then this becomes 3. So 1/3 ml squared. So this is the moment of inertia of the rod. Okay, now we know moment of inertia, then we know alpha. Then simply we can find the torque, which is I alpha. So I is ml squared, alpha is omega divided by time, right? Then you need to arrange them according to the answer. So what do we have? ml squared omega divided by 3t, right? So this is the torque. Got it? Answer is second one. So if you have practiced the linear motion questions, these questions are similar to them, right? You are doing the same thing. Instead of that distance, you are just putting the angle. Then instead of the mass, you are putting the moment of inertia. So that is the only difference there. The equations looks a bit complicated, but you are just doing simple calculations, right? That you learned in O levels. Right. Then we'll move on to 13th question. A uniform rod with length L is pinned from one end of it. So it is, let's say, pinned at A. One end of it's free to rotate around that end, right? So it is like this, right? It's pinned here. Other end is free to rotate like this. When it is held horizontally and released, initial angular velocity, angular acceleration of the rod is. So let's say initial angular acceleration is alpha. So if you mark the forces, so let's say this has a mass m, simple m, and the only force is mg, right? There's no any other force here. So I'm going to take moments, I'm going to apply this equation, tau equals I alpha around A. So whenever you apply this equation, you have to consider around which axis that you're applying that. So it is around A, axis going through the point A, right? Perpendicular to the rod, right? So the forces from at the point A, we can neglect those forces because there's no distance to those forces from the axis. So the only force becomes mg, right? So mg, perpendicular distance is, so they have given length as simple L. So this distance should be L over 2, right? They say the moment of inertia, it is not given. So in this case, the equation for moment of inertia for a rod like this is 1/3 ml squared. You should remember that. So for an axis through the center, from the middle of the rod, it is 1/12 ml squared. But for if the axis, rotational axis at one end of the rod, the equation is 1/3 ml squared, right? It is not 1/12, 1/3 ml squared. Then you have the alpha, right? Then you need to find alpha, I think, yeah. Then just simplify. M cancels off, we have get 3. 1L also you can get rid of. So here 3G divided by 2L, right? So this is alpha. This alpha is actually initial, right? Initial. Why do they say initial acceleration? Initial angular acceleration. You can see this acceleration changes, right? This value is only for when the moment that the rod is released. Still the rod is horizontal. But what happens when it inclined like this? Mg is here. So see that this distance has decreased. So the torque decreases. So alpha decreases, right? Gradually alpha decreases as it falls down. So that's why they say initial angular acceleration, right? So for this question, you cannot apply motion equations because those motion equations are applied only for constant angular acceleration. Remember, it is similar to linear acceleration, right? Those equations were applied only for constant acceleration. But here we don't have a constant acceleration. Acceleration decreases as it falls down. As it moves like this, acceleration decreases, right? So when you're doing questions like this, for each point, for each instant, you can apply rho equals I alpha or energy equations when you get a question like this. You cannot apply motion equations. Remember that, right? Right, 14th question. Moment of inertia of Earth is capital I and its radius is capital R. Moment of inertia is I, radius is capital R, and angular velocity is omega. If it is to be stopped within a capital T time, tangential force required is, let's say you need to apply tangential force to this side, right? Let's say on the circumference, right? Tangential to the surface. You have to apply this F to the other side, right? So it creates a counter torque to stop the Earth. So what they ask is that tangential force required. So how do you find that? So if in order to apply tau equals I alpha, we need to find alpha, right? I is given. So first I'll just apply this equation. So finally it has to stop. Initial velocity is omega plus alpha t. Let's say I apply this to this side, right? Then take this equation to here. So alpha becomes minus omega divided by t. So this is the angular acceleration. So to this side we got a angular deceleration. But to the other side, if you want, you can take it as angular acceleration plus, right? You can change the sides and make it a plus. Right. Then I'll apply tau equals I alpha. I'm going to apply to this side, right? To the other side. So to the other side, force and that is a positive. Force times R is a positive. Plus equals I. They have given I as I. Then alpha. So to that side, alpha you get a positive value. Omega divided by t. So what they ask is F. So put R here. I omega divided by dr. So that is the tangential force required. I omega divided by dr or rt. Actually this t is capital T, right? They say capital T, right? Not simple T. So it should be tr, capital TR. So here the specialty is you need to think about these directions as well, right? When you are, especially when you are doing an essay question, you need to think about these. Similar to those linear motions equations, when you apply linear motion equations, you consider those directions. Here as well, you can consider the directions. So without any confusion, you can get the answer there. See that? You got a positive answer there, right? So if you change the direction, if you counter the direction, you know that minus becomes plus. Okay, so that is just basic vector. So that is vector knowledge. So you know that these quantities also are vectors, right? But for rotational quantities, usually we don't, it is not proper to show the direction of a vector like this. To like this, vectors needs to have a certain direction, right? Therefore, for these rotational quantities, so let's say the object rotates to this side. So what do? You get the right hand and these fingers shows the direction of the rotation. And thumb shows the direction of that vector. So this is, if it is rotate like this, so this is counterclockwise, right? This is anti-clockwise. To me, as I am seeing, it is counterclockwise. Then the direction of that rotation, we take it as to this direction. So it has a certain direction. So that is the scientific way to define the direction when you are considering rotation, angular quantities. Okay. So let's say move into the clockwise direction. So the direction of that quantity should be here, right? Like that. You can consider that. You have to learn those in theories. So that is the scientific method to find the direction of angular quantities. Right. 15th question. A wheel with mass 40 kilogram, 40 kilogram and radius 0.5 meters is rotating at angular velocity 1800 rpm. Then it is stopped by applying a constant torque. So torque is applied within 30 seconds. Within 30 seconds it is stopped. Magnitude of the torque is, right? So this is rotating, already it is rotating. Then you apply a counter torque in order to stop this, right? First, I'll convert this into radius per second. So 1800 r means 2 pi, right? Per minute means you need to divide by 60. 30 times 2, 60 pi rad per second. So this is the initial angular velocity, omega naught. So here we need to find the angular deceleration. So I'll use a motion equation. Finally, you need to stop that. Initial velocity is 60 and I take positive direction as to this direction, right? 60 plus alpha. Time is given as 30 seconds, right? So alpha is minus 2 rad per square second. 2, right? Take it to the other side, minus. Alpha is minus 2 radians per square second. Okay. So this is to this side. But to the other side, it is positive. Right? Okay. So what they ask is torque, right? So before finding torque, we need I. Alpha we found, but we need I as well. So this is a wheel, meaning the total mass is at the edge. So you can use mr squared. So mass is 40, radius is 0.5 squared. 0.5 means half. Half squared means 1/4. When you multiply that, 10 kg meter squared. Then just apply this one. I'm applying to this side, right? It doesn't matter which direction you apply as long as you are considering these vectors, right? Right. So torque is what we need. I is 10, alpha is 2. It is positive, right? Because I applied to this side. So it is 20 Newton meters. 20. There's a 5 here, right? 65. I could forget the 5. So there's a 5 here. So you get 2 pi there. So it should be 20 pi Newton meters. Don't forget that pi, right? Here you have a pi. Pi means if you want, you can substitute as 3.14. But in the answers, they have just used 5 as 5 pi. So it is just 2 pi Newton meters. Sorry, 20 pi Newton meters. So the second one is the answer there.